Hello, everybody. Welcome to AP Chemistry Chapter 5, Bonding. This would be our first chapter of our second unit. So we just finished Unit 1, took our test on that, and this is our next section. This entire unit, to kind of summarize what we'll be doing over the next couple chapters, is all about, well, bonding in this one, meaning atoms bonding together to make compounds, about intermolecular forces, which are the forces between different molecules, why they stick together, their boiling points and melting points and all this information, and gas laws as well. This is actually a very big section for the AP exam. Bonding and intermolecular forces, somewhere around 25% of the exam, maybe even 30%. So it's a very important sort of topic. Okay. Today we're specifically talking about bonding, which is going to include a couple things, namely types of chemical bonds, meaning ionic and covalent bonds, and a little bit about metallic bonds, but not really yet. Intramolecular forces, and drawing Lewis diagrams. So we'll get to do some drawings of those today. Okay, so to start, we have this word intramolecular force. And intra, we can think about that prefix intra. It kind of means like inside, right? So like an interstate, like our interstate goes between states, connects multiple states. But that's not what this is. This is an intra. An intrastate road is a road that's contained inside one state. You can use it to get around just Florida or something, but it doesn't connect multiple different states. So an intra is like things that connect the inside of one object to each other. And that's what we're going to apply to molecules, because the intramolecular force is the force that holds together molecules. Compare that to an intermolecular force. That's when you have many molecules and they're all connected to each other. They're all held together in some sort of structure as a solid, liquid, or gas. But we're not getting to those yet. We will in this unit for sure. But this chapter talks about intramolecular forces only. Okay, so this is like, why do molecules stick together? What forces are going on there? The intramolecular force holding together an ionic bond is the Coulombic. There's that word again from last couple of chapters, Coulomb's law. When you see that, you're just thinking positive and negative attract, or like charges repel. Okay? So an intramolecular force that holds together an ionic bond is that Coulombic attraction between the positive and negative ion. The intramolecular forces holding together a covalent bond is more complicated. If you're not familiar, don't remember those words, we will definitely go over them. But we just want to kind of start with a little bit of a brainstorm. So I have two atoms here. I have a nucleus in the middle, right? And I have my electrons here on the outside. And we just want to kind of talk about what are the repulsive and attractive forces in this picture. So to kind of think about it, I have a couple of atoms I've drawn here. The idea is if I have just two atoms by themselves, and this has just some protons in the middle, so a positive charge and a negative charge on the outside, and I have another atom over here, what are the reasons these things would like to be together, or would they prefer to be apart? And there's more complicated ways to think about this as we go, but just as kind of to start us here, let's think about if we get these things close together. There's some good things going on here, and there's some bad things going on. So there's kind of a mixture of attraction and repulsion. Our nucleus, our positive charge over here, likes negative charges. So it's happy that this negative charge over here is close to it. But these negative charges here don't like each other. So there's some repulsion there. And if I keep getting these closer, the positive charge and this positive charge repel each other. So I want to get these close a little bit is kind of the idea, because the positive and negatives of the adjacent atoms like each other. So like this nucleus likes this electron and vice versa. This nucleus like this electron. But as you get them too close to each other, these nucleuses get too close to each other and those repel each other. So there's just kind of an interesting combination of when I'm bonding two atoms together, there's going to be some perfect kind of sweet spot distance where you kind of balance out the attraction and repulsion of these things. So atoms like to get really close to each other, but they can't be too close, for example. Because if you start to try to overlap the nuclei, the actual solid part of the atom, right, you can't overlap solids. So if I try to get these nuclei too close to each other, okay, that's not going to work out very well. So that's kind of what's going on here. There's a balancing act between the positives and negatives of two adjacent atoms. Some parts of them want to be attracted, some parts want to be repelled. Another idea is if these things are all the way apart, on the other side of the world from each other, then they'll be experiencing no attraction or repulsion. As you increase the radius between two objects, the force of attraction and repulsion goes down to zero. So we would say that these two objects are too far away from each other and they don't attract or repel each other. But as you bring them closer, the attraction goes up and the repulsion goes up. So we'll kind of talk about that with a graph we're going to show you in just a bit. So this leads us to the idea of bonding. There's a characteristic bond length for every molecule, meaning there's kind of that perfect sweet spot distance that those two atoms will like to join at. That's kind of the part that like optimizes the attractions and minimizes the repulsions to be in the lowest possible energy state available. This means that every molecule has a particular length based on the energy of it. So over here on the right, I have some examples of these. Two hydrogens, for example, will bond at a length of 74 picometers, which is a super small distance. And all these different atoms, you can kind of see their bond length, and they're kind of increasing as you go up here. Okay. One thing you might notice, hydrogens are really, really tiny. They only have one proton and one ring, right? So they're really small, and they have a really small length. They can get closer to each other, which might make sense if you think about the fact that they're smaller. They can get a little bit more snug to each other, right? They don't take up as much space individually. This bond length is technically the distance from the nucleus of one to the nucleus of another. So smaller atoms can generally get closer to each other, and that's going to be important. Okay, as you go down this list, we're starting to get some bigger atoms. By the time we get to the bottom, we have iodines, which are quite large, and bromines are pretty big as well, and you're seeing that bond distance going up. We also have something over here, the average energy. Okay? So this energy, it's in kilojoules per mole. So this is meaning how many kilojoules of energy does one entire mole of these particles, how much energy would it take to break that bond is essentially what this is saying. Okay, so this is saying like if I had 1 mole of H2 molecules, it would take 432 kilojoules of energy to split them all apart, to break all those bonds. Okay. Bonds are essentially like, you hear it talked about a bunch of different ways, but they're a low energy arrangement. It saves energy to make a bond. Basically, when these two things bond together, the product is lower energy than what you start with. So it releases energy when you make them. So to break them, you need to add that energy back. And that's what this numbers kind of is. So why are the bonds these lengths, and why do they have different energies associated with them? Let's kind of talk about it some more. Okay, this graph over here is really important for this chapter. This is a whole topic in the AP classroom sort of thing in our curriculum map. Is all this graph essentially. Okay, it's called the potential energy of an intramolecular force. Okay, this graph is a measure of the potential energy of two atoms making a bond. The bond will find the equilibrium point that is the lowest in energy. This point is the balance between the repulsive forces of the two nuclei and the attractive forces between each other's protons and electrons. So let's try to interpret this graph just a little bit. Okay. So we have potential energy on our y-axis, meaning if you go above this line here is actually going to be 0. It's not labeled here, but this axis is 0. So this is no energy at all, right? And you'll notice if you increase r over here is what this axis is. This distance r is how far apart the two atoms are. And so over here left, this would be 0 picometers apart, meaning they would literally be stacked on top of each other. And as you go to the right, you're increasing the distance of the two atoms. So this is 74 picometers, and that will be important. But as you keep going to the right, you'll notice the energy approaches 0. Like we said, if you have two atoms completely separated from each other, they're not attracting or repelling each other. So they have 0 energy to each other, essentially. So you'll notice this asymptotically approaches 0 as you move the particles apart. So this line is kind of the energy of related to the distance between the two atoms. So over here on the right, your atoms are completely split apart. And as you start to bring them closer to each other, like I was doing on the paper, there's some attractive forces going on here. Having the two atoms next to each other nets a little bit of attraction. So all of this, you're seeing you're getting more and more attracted as you move them closer together until you get to a certain point. This point, which is at exactly 74 picometers for these atoms, meaning it's an H2 atom, okay, is the maximum, the most attractive forces you can have. And you'll notice after that, the energy starts to go down. or I guess go up in this case, but like it starts to go away from this bottom and eventually goes to zero, and then even past zero, all the way up positive. That's because there's some repulsive forces. As you're getting those atoms too close to each other, the nuclei are getting too close to each other, and they're repelling each other a lot. They don't like that. Okay, so you have this, like I've said this word like 10 times already, but you have this balancing act between the attractive forces of the protons and electrons of the adjacent atoms wanting to be near each other. But then once they get too close to each other, those two nuclei really start to repel each other and will push away, make some repulsive forces happen. The main things we need to take from this is that there's this perfect sweet spot, and that distance is the bonding distance, the bond length. That is the distance that these two atoms will always choose to bond. You'll notice over here, if we look at the energy, it saves it saves 436 kilojoules per mole. And that's why it's a negative number. You actually would, when this bond is made, release that much energy. And that's what that negative means. Okay? So making these two things bond together saves 436 kilojoules of energy. So those are kind of the two main points here. So we have the amount of energy saved will be on the y-axis, and then the bond length will be here on the x-axis. Okay, so this is kind of describing this a little bit more in words for you. Atoms will only bond if it reduces the total energy of the system. That is the reason that they are bonding, just because it's energetically favorable. Arranging the atoms in a bond instead of as separate atoms decreases their total energy in this example by 436 kilojoules per mole. Okay? If I added up the energy of these two individual atoms, it would be 436 kilojoules per mole more than if I bonded them together. But when I bond them, that energy has to go somewhere. Energy cannot be created or destroyed. It can only change forms or move somewhere else. Okay? That means when these two things bond, that energy that you're saving gets released into the environment. Right? It gets released as heat. When these two atoms bond, they release 436 kilojoules per mole of energy. And then if I wanted to split them apart again, I would have to apply some energy to that bond to break it. This specific bond, if I wanted to break 1 mole of bonds of them, would take 436 kilojoules of energy. So kind of this is summarizing that idea. You have two individual atoms, atom A, atom B. Atom A has 10 energy points. We're not using real units here. Atom B has 10 energy points as well. So each individual atom by itself, maybe it's their same atom. Maybe they're both hydrogens again. Doesn't really matter. But they each have 10 energy points by themselves. Okay? But if they form a compound, that arrangement, because of all the positive and negative attraction, the Coulombic forces there, the overall energy would decrease. This compound only has 15 energy points total. They choose to join together because it saves energy. That excess energy, or that leftover, that remainder of energy you had left over, has to go somewhere though, so that 5 energy is released to the environment, usually as heat. Now to break the bond, I must add at least 5 more energy to the compound to return the atoms back to 10 energy each. Okay, so I can't just split this apart without adding a little bit of heat to let them both be back at their original energies. So to kind of summarize bond energy here, a bond is made as a result of attraction between two atoms. When bonds are made, energy is released because the energy of the compound is less than the energy of the individual atoms. And to break a bond, energy must be added to it. All right, so our example here, what is the bond length and enthalpy of the element below? So this is the only type of graph you'll ever see. You'll see this exact same looking curve for all sorts of different atoms, and we'll have a couple examples today. So we have this curve, it goes down. We're looking for the energy minimum, which looks like would be like here-ish. So the bond length would be whatever distance that is. So it looks like that would be about 75 picometers would be my guess, because it's between, this looks like 50 and 100. So I would estimate that about 75 picometers. Okay, and the enthalpy is a fancy word we haven't quite worried about yet. But it's just, think about it now as just energy. It's the energy you would need to like break that bond. So that's just what we're going to look over here on the other axis for. So 75, and then that would lead us to be about maybe negative 450 or so, maybe a little bit more than that, negative 475, something in that range. And that's what we could write as our enthalpy. And for now, that's all you really need that word for. All right. And it also asks, why does the line not go all the way to 0 picometers? You see it stops here. Okay. Well, the idea there is once you get to whatever distance this is, say it's 35 picometers, the nuclei are starting to actually overlap each other. They're completely coming into the middle and starting to touch and then overlap. And that is really bad. Matter is not allowed to overlap. Okay? So not only are they repelling each other as you get them closer, you can't stack matter on top of each other, which is why you can't have them 0 picometers away. That would literally be them being on top of each other. And that's bad. That doesn't work with physics. All right, we've talked about valence electrons a bit, but to kind of summarize, and we're going to need them a lot for this chapter and the next coming chapters. Valence electrons are the most important electrons. They're the ones that form bonds and react with other atoms in chemical reactions. The valence electrons are the furthest from the nucleus. They have the highest energy levels. These are all different kind of ways to talk about valence electrons. If you write an electron configuration, the valence electrons are all the electrons in the highest energy level, meaning the highest, like, big number before the S, like 4s. Okay? All of the electrons in your highest number are your valence electrons, the ones furthest away from the nucleus. These are the first to be removed because they have the lowest ionization energy, is one way to say it, or they're just the easiest to remove. It takes the least energy to remove them. So we need to be able to quickly determine how many valence electrons are in some different atoms. So we can break it down in a couple different ways. There's lots of different ways to figure it out. And at the end, I'll show you a shortcut to make it a lot simpler. So if I have these two atoms, I want to figure out how many valence electrons they have. First way I can do it is I can write out the electron configuration. I can write out for aluminum. Let me focus on that a little bit better. Give it a second there. I'm going to start just kind of writing 1s2, 2s2. That usually helps it pick it up. There we go. 2p6, 3s2, 3p1. Work with me. Work with me. Zoom out a little bit. What you doing? Oh, no, back. No. Okay, this is very professional. Okay. Let me pause for a moment. Okay, all I had to do is write out real words, called it an idiot, and then it focused. I don't know what that's about. So let's look at our valence electrons here. Like I said, we're just gonna look for our biggest number, which is 3 this time. And I actually have it 2 different spots, which is totally okay. So I have 2 electrons here. That's what that 2 means, and 1 here. That means I have a total of 3 valence electrons. Now I could do sulfur as well. Sulfur's 1s2, 2s2, 2p6, 3s2, 3p4. Again, 3 is its highest number. This time it has 2 plus 4 equals 6 valence electrons. And that's cool. You could do that. But there's a lot simpler way to figure out valence electrons, and it actually uses your periodic table. Based on the position of the element on the periodic table, you can just simply tell how many valence electrons it has. And that's what this table here is doing for you. So you have 1 valence electron for all the alkali metals, everything in this column, 2 for everything in this one. We skip the middle because there's a couple we'll need to know eventually, but they're kind of random. They don't have a nice pattern. So we just skip over to here to 3, 4, 5, 6, 7, 8 in the last row, with the exception of 2 for helium because it's so small it doesn't quite have 8 yet. So it's kind of our weird outlier in this trend. You'll notice this is the exact same number as effective charge you wrote on your periodic table last time. Effective charge is just another sort of way to think about how many valence electrons you have. Those numbers will always be the same. Even though they're not really saying the same things, it just kind of works out. The math works out that way. So make sure you have on your periodic table and you kind of remember this idea. You can just quickly look at aluminum, for example, is here. Okay. and sulfur is here. So I wouldn't even need to write its configuration. I could just look at its spot on the table, figure out how many valence electrons it has that way. So valence electrons are important because it actually determines what likes to bond with what. Atoms will bond to form compounds to completely fill or completely empty their valence shells. So both those base atoms I just showed you did not have full valence shells, right? Both of their p orbitals were not full or empty. They're kind of like this intermediate state. If this was full, it would have to be like a 6, right? If this was full, again, it would have to be a 6. There's something about having a full, what we're going to call octet, being completely full of valence electrons, it turns out, is a whole lot more stable. Okay? Having a full or empty, we're going to learn it kind of means the same thing, because if it's all empty, that's not actually your valence shell anymore. Your valence shell is now your next one down, and now that one's full, because the one above it is empty. Okay? So being full or empty, losing or gaining electrons up to 8 or down to 0 is going to end up being the same thing. Okay? Having a full or empty valence shell is the most stable because it's the most symmetric. Atoms want to be symmetric because it's the lowest possible energy arrangement again. So sort of that same keyword or lingo energy arrangement we're using with bonding, we're using again here. This means that atoms usually want to have either 8 or 0 electrons, and this has an official name. It's called the octet rule. Okay, think of an atom like a ceiling fan. Okay, so you have all these different blades whirling around, and ceiling fans work really well, right? They're spinning around really, really fast, right? But they wouldn't work very well if you were to remove one of the blades. So imagine taking off one of these entire blades, you'd be left with 3 fan blades, and the weight would be off. You would have some blades on one side and not a blade over here, so the weight would be heavier on the other side, and every time it'd spin around, it would kind of like wobble. And same thing, if you keep removing blades, if you only had one blade, for example, if you just had one blade, it would do the same thing. The only way a fan is stable is if all the blades are there. And it's kind of the same thing with electrons in orbitals. They're spinning around super, super fast, and you can kind of think of them the same way, right? If they're spinning around and it's nice and symmetric, they don't have that sort of wobble or spin that they might have had otherwise. Now, we also said it's perfectly stable if you remove all of the blades as well, if you remove every electron. And your fan would spin just fine if it had no blades. That'd be another way to have equal weight on every side. That would cause another problem, like it wouldn't be a very good fan, but like that would still be very stable. Okay? So think of that as kind of your reasoning for why atoms want to have either full or empty electrons. Think about them whirling around really, really fast and wanting to keep that weight even. Okay, so more on the octet rule here. Atoms will bond in ways that satisfy the octet rule for every single atom in that bond, in that compound. Atoms need to get creative with their electrons to make them as stable as possible. They can do all these different things to kind of manipulate the number of electrons they have. They can share them, they can accept them, meaning take them from other atoms, or they can donate them to other atoms. But it's important they will only bond in ways to make the entire system more stable. They're only going to bond in ways to lower the energy. We have our 3 types of bonds here today. We're really going to focus on the top 2. The last one's kind of for another day. Bonding is classified into 3 main types. First, you have ionic. Traditionally, between a metal and a nonmetal, there are some exceptions, but we'll talk a little bit about that actually later today. Ionic bonds are a transfer of electrons, and that part is not an exception. Every ionic bond is one electron being transferred or multiple electrons being transferred from one atom to another. So that means one is completely losing electrons and one is completely gaining electrons. It comes from the word ion, and we know that an ion is just an atom that has gained or lost electrons. So that's where the word ionic comes from, and that's how you can associate it. Covalence, a little more complicated. This is when you usually have multiple nonmetals. Now, nonmetals are the very top right part of your periodic table. And we learned that nonmetals are very electronegative, meaning they want to gain electrons. And we also learned they have a high electron affinity, which means kind of the same thing. They really want to gain electrons. So you don't have the situation where one is okay losing electrons and one's okay gaining electrons. They both want to gain more electrons. And that's because they're both close to filling their valence shell. Nonmetals are on the right side of the periodic table, so they mostly have like 6 or 7 or 5 valence electrons. So it's going to be easier for them to gain electrons together. They want a way to increase their electrons for both atoms bonding. And they do that by sharing them. They can actually each kind of like put up one of their own electrons in the middle and kind of get really close to each other and kind of share their 2 electrons together. And that's what a covalent bond is. So when each atom contributes one atom to a bond, and the atoms kind of sit in really close to each other, so they can each experience the electron pair together. And metallic is between 2 metals, and it's really weird. So we'll talk about that a bit later. I'm not really worried about that for today. They don't bond in traditional ways like ionic and covalent things do. So here's kind of what I was saying. Here's your metals, nonmetals, and metalloids on your periodic table. So the idea is we can kind of think about what these things want to accomplish. Over here on the left, and the easiest examples are these first 2 rows, because lithium has 1 valence electron along with everything else here. Beryllium has 2 valence electrons along with everything else here. So the easiest way for these things to satisfy the octet rule, they can either choose to have 0 valence electrons to get to empty shell, or get up to 8. And because they're on the lower end of the spectrum here, it's a lot easier to lose 1 electron or lose 2 electrons than it is to gain 6 or 7. So they tend to lose electrons in chemical reactions, and that's actually true for all these metals. All these metals generally prefer to lose electrons instead of gaining them, because that's an easier way to accomplish their goal of being stable. On the right side, you have all these blue nonmetals, and these yellow ones are called metalloids, but we kind of treat them as nonmetals as well. You won't really do much with most of them. These top 2, boron and silicon, are used pretty often. Those just kind of treat them like they're other nonmetals, but there's some weird things about them that don't really apply to us yet, though. The idea is these things all have between 4 and 7 valence electrons, so they all want to gain electrons. So when they bond with a red thing, they're happy with that. They want to take their electrons. Sodium, for example, really wants to give its 1 electron to fluorine, because fluorine only needs 1 electron. So those 2 things make great partners for a chemical bond. They can accomplish their goal together. Okay. When we're talking about covalent bonds, you have multiple of these atoms, and you don't have a situation where one wants to give and one wants to take, so they end up sharing instead. All right, the type of bond formed is determined by the difference in electronegativity between the bonding atoms. So, a large difference causes the more electronegative atom to take the electrons completely away. You have one very electronegative atom like fluorine, and one low electronegativity atom like maybe sodium again. That's when you're going to have an ionic bond. One is so much more electronegative. It wants that electron so much more that it's able to completely steal it away from the sodium. And the sodium's chill with that because it wants to lose that one anyways. So that's the sort of situation that leads to a complete transfer of electrons. But if that difference is much smaller, then one atom can't completely take an electron away from another atom. Right? A small electronegativity difference, like between multiple nonmetals, creates a covalent bond, a situation where they'll share electrons. And this explains why nonmetal to nonmetal is usually covalent, although there could be exceptions, and metal to nonmetal is usually ionic, because usually metals have low electronegativities and usually metals or nonmetals have high ones. A lot of the time, though, bonds aren't purely either of these. There's kind of a spectrum of how covalent are you? Are you pure covalent, or are you polar covalent, we're going to learn about? Or are you ionic, and how ionic are you? Sometimes a covalent bond shares electrons, but it doesn't share them equally. There's a spectrum that demonstrates how ionic or covalent a bond is what that should say. Okay. The spectrum depends on the difference in electronegativity between the 2 atoms. So here is our idea. The difference in electronegativity between your atoms is just going to be like, each atom will have a number, and you subtract them to get the difference. If that difference is really small, meaning less than 0.4, that's a pure covalent bond. We treat them as 2 atoms sharing their electrons completely the same. If it's above 1.8, we consider that a large difference in electronegativity, and that bond will be purely ionic, meaning one electron will be completely stolen away from the other atom. But you have everywhere in between those two numbers, you make a polar covalent bond. It's a covalent bond still, they're still sharing electrons, but they're not sharing them equally. The more electronegative atom is hogging the electrons to itself. We can kind of see that here. So if no difference in electronegativity occurs, these two atoms share that electron space equally. So you can kind of think of the electrons being here in the middle, and all this purple area is kind of where the electrons are allowed to be, and they're sharing them completely equally. But in the middle here, a covalent polar bond, they're not being shared equally, right? This atom over here is taking more of the space and leaving only a little bit of space here for the other atom. The electrons, you can think about it being in the purple or pink area randomly, but it spends a lot more time over here in the purple because there's a lot more space for it to be. In an ionic, it's not like that. It's a complete transfer, right? The entire purple goes over to the more electronegative atom, and the positive atom is left with none of it. So, next is ionic bonds. An ionic bond is a transfer of electrons from one atom to another. Once the atoms transfer electrons, they become oppositely charged ions that are then attracted to each other. So our last example had some positive and negative charges drawn on that last one. Okay, so real quick, positive and negatives. Okay, if you transfer electrons, now you're attracted to each other. And that's basically all an ionic bond is. When electrons are transferred, afterwards your result is a positive and negatively charged thing, and they stick together because of that. I have some orbital diagrams here of sodium and chlorine, although these are backwards. Let me pause. We have sodium and chlorine, and they're not backwards. Okay, so sodium up here on the top, it has. Oh my God, this is not sodium. One moment.